Hello everyone, welcome to the class. Today we will start the next module, which is module number 10. In this module we will talk about Brewster's law and Malus law. Thereafter I will introduce you the phenomena of double refraction, which is very interesting phenomena, and then we will talk about normal and oblique incidences. We will see that what would be the path of the ray if it is met to incident normally and obliquely in double refracting media, and at last we will talk about production of polarized light. Today in this lecture we will only talk about Brewster's law and Malus law. Now, the first topic which we will cover is Brewster's law. For this, consider an electromagnetic wave which is falling on the interface between the two dielectric media. Now, in electromagnetics we talk about Fresnel equation which governs reflection and refraction in different kind of dielectric material medium. Now, Fresnel equations relate the reflected and transmitted field amplitudes to the incident amplitude by the way of angles of incidence and refraction. The angles of incidence is represented by theta I, while angle of refraction is represented by theta r. Now, suppose that the light which we met to incident on the interface is linearly polarized, and the polarization is such that the field E is parallel to the plane of incidence. Okay. Now, if you are confused with the plane of incidence, then we will revisit this concept. Suppose these are the two this is the interface, and N1 and N2 represents the refractive indices of the two media. Now, if a light falls on the interface at some angle theta, then the plane which have the incident light, the perpendicular and this point of incidence, this plane is called plane of incidence. Okay, I repeat, the perpendicular and the ray, they both would be in the plane of incidence, and of course, if the two lines are there in the plane of incidence, the point of incidence would also be there in that plane, because using two lines we can generate a plane. Okay, the normal to the point and the incident ray, using these two lines we can generate a plane, and this plane is called plane of incidence. Okay. Now, if a linearly polarized light with electric field in the plane of incidence is now launched, then following Fresnel relation we can give an expression of reflectance in such a case, and the reflectance for a given polarization is given by equation number 1, which says R parallel is equal to tan square theta I minus theta r upon tan square theta I plus theta r, okay, which is a symbol of parallel. Yeah, R parallel represents that polarization is parallel to the plane of incidence. Okay. Similarly, suppose we have a linearly polarized light whose electric field is perpendicular to the plane of incidence. In that particular case, from Fresnel relation we can again derive the expression for reflectance for this perpendicular polarization R perpendicular, and this is given by equation number 2, which reads as R perpendicular is equal to sin square theta I minus theta r upon sin square theta I plus theta r. Okay. These two equations are very important. This represents reflectance for a light which is polarized in plane of incidence, and reflectance for a light which is polarized perpendicular to the plane of incidence. Now, in equation 1 and 2 you see that these are the expressions for reflectance for a light which is whose electric field is parallel to the plane of incidence, and equation 2 is expression of reflectance for a light which is whose polarization is perpendicular to the plane of incidence. Now, in the denominator in equation 2 is a function of sin. You see, in the denominator we have sin square theta I plus theta r, and sin theta varies from 0 to 1. Yeah. Therefore, R perpendicular can never be equal to 0, it can never go to 0. while in equation 1 we see that the denominator is sin tan square theta I plus theta r. It is a tan there in the denominator, and which can assume infinity value also. When theta I plus theta r is equal to 90 degree, then tan of 90 which is equal to infinity, and then in that particular case r parallel is equal to 0. It means if we launch a light at the interface between two dielectric media at an angle which is defined in such a way that theta I plus theta r is equal to 90, then there would be no reflectance. Okay. Therefore, r perpendicular can never be 0, while r parallel is indeed 0 when the denominator is infinite, that is when theta I plus theta r is equal to 90 degree and tan 90 is infinity. Therefore, equation 1 can go to 0, r parallel can be 0. The reflectance for light with E parallel to the plane of incidence thereupon vanishes, because E r parallel is equal to 0, and therefore, the beam is completely transmitted. Okay, we are launching a light at a certain angle of incidence and which is having a polarization which is parallel to the plane of incidence. In this particular case, there would be no reflectance, there would not be any reflected light, and therefore, what will happen is that all the light will go into the second medium, all the light would be transmitted. Okay. Now, the third point is that if an unpolarized beam is incident at an angle such that theta I plus theta r is equal to 90 degree, then the parallel component of E will not be reflected, and reflected light would be polarized with its field E field perpendicular to the plane of incidence, and this is known as Brewster's law. I repeat, if we launch an unpolarized light at an angle such that theta I plus theta r is equal to 90 degree, then in this case the parallel component of field will not be reflected, it would be transmitted totally, and therefore, in the reflected arm we will have a light whose polarization, whose E field is perpendicular to the plane of incidence, and this is exactly the Brewster's law, and the corresponding angle of incidence is known as Brewster's angle. Theta I, this particular theta I is called Brewster angle and is usually denoted by theta p. Now, let us apply Snell's law here. Since theta I plus theta r is equal to 90 degree, and when the Brewster law is satisfied, then theta I would be equal to theta p. From there, the angle of refraction would be given by pi by 2 minus theta p. I repeat, in this particular case, the angle of refraction would be pi by 2 minus theta p, and therefore, the Snell's law takes the following form: n2 by n1 would be equal to sin theta I by sin theta r, but sin theta r is equal to pi by 2 minus theta p, which is nothing but cos theta p, and therefore, on right hand side of equation 3 we will have tan theta p, and from here we can calculate the value of theta p, which would be equal to tan inverse n2 by n1, and theta p is Brewster angle. Okay. Thus, the angle of incidence is equal to tan inverse n2 by n1, okay. And when the angle of incidence is equal to theta p, the reflected beam is plane polarized, and further the transmitted beam is partially polarized. At the polarizing angle, the reflected ray is at right angle to the refracted ray, and this is shown here in this figure schematically. In this figure, we have two media of refractive indices n1 and n2 respectively, and an unpolarized light is launched from medium of refractive index n1 into medium of refractive index n2, and at the interface, if the angle of incidence is equal to theta p, the reflected light will have only field component for which the polarization is perpendicular to the plane of the paper, while the transmitted light will be partially polarized, because it will majorly have field components which are parallel to the plane of incidence. Okay. And therefore, if we launch an unpolarized light in the reflected arm, we will have a linearly polarized light whose field component are perpendicular to the plane of the paper, are perpendicular to the plane of incidence, because the fields which are in the plane of incidence are not allowed to get reflected. Okay. And therefore, all these field components will reflect in this transmitted arm, and this transmitted part or this transmitted light would be partially polarized. Okay. We can again filter the polarization from this transmitted light by putting more layers of material and arranging them in such a way that this light also falls at this theta p angle, the Brewster angle, and then there will be multiple reflection and transmission, and each reflected light would be linearly polarized, and the transmitted light would be filtered, it would get more and more polarized. Yeah. And this is all about Brewster angle. Now, we will start another topic, which is law of Malus or Malus law. Now, suppose you launch an unpolarized light on a polarizer, on a device which is called polarizer. When a unpolarized light is met to incident on the polarizer, then what does polarizer do is that it makes this unpolarized light, it converts this unpolarized light into a linearly polarized light. How does it do so? It has some arrangement of polymers which allows only a certain polarization to pass through. Okay. It has pass axis which is oriented in a certain direction. Say the pass axis is oriented along my fingers, therefore, it will allow, this particular polarizer will allow only polarizations which are oscillating in a vertical direction. Okay. The field component which is oscillating this way is only allowed to pass through this polarizer. Okay. And therefore, if we launch an unpolarized light, then only component which are oscillating along this pass axis of the polarizer, pass axis means the axis along which the light is allowed to pass. Yeah. Now, consider a polarizer P which has a pass axis parallel to x axis, okay, and say x axis is vertically up, and if an unpolarized beam propagating in the z direction we assume as the direction of propagation, is incident on the polarizer, then the electric vector associated with the emergent wave will oscillate along x axis, that is pass axis of the polarizer. Now, consider the incidence of x polarized beam on the polarizer P2, which is the next polarizer, which is coaxially placed with the first polarizer, whose pass axis makes an angle theta with the x axis. Okay. Now, we are considering two polarizers, and the pass axis of first polarizer is along x axis, while the pass axis of the second polarizer is rotated. Okay. It is making an angle theta with the vertical, and they are coaxially placed. Okay. Now, as I explained before, if we launch an unpolarized light, the polarizer will allow only those field components which are oscillating in vertical direction for this particular polarizer, okay, and rest of the field component would be stopped. And the present case, we are considering two polarizer which are rotated by theta degree. Now, if the amplitude of the incident electric field is E naught, okay, then the amplitude of the wave emerging from the polarizer 2 would be E naught cos theta. Okay. And therefore, if you want to calculate the intensity of the emerging beam, then this would be given by this relation, I is equal to I naught cos square theta, where I naught represents the intensity of the emergent beam when the pass axis of P2 is always along x axis. And this equation, equation number 5, is called Malus law. Now, we will try to understand this concept schematically through these figures. Now, we know that in unpolarized light, the electric field can randomly orient itself in any direction, and therefore, unpolarized light is schematically represented by this star type figure. Okay, this is double headed arrows and which represents the direction of oscillation of the field, and since the field can orient in any direction, this star shaped field symbol is chosen to represent unpolarized light. Now, suppose this is unpolarized light which is being launched on this polarization P1, and the path axis of the polarizer is along x axis and the direction of propagation is along z axis. As I said before, the polarizer only allows those fields whose direction of vibration is along the path axis of the polarizer. Therefore, in this figure, the field components which will pass through this polarizer are those which oscillates vertically. Okay. Therefore, only this vertical oscillating field will come out from polarizer P1. Okay. And we see here that we are launching an unpolarized light, and after polarizer P1 we are getting a linearly polarized light, because the light which is coming through P1, it has a field component which is only oscillating in the vertical direction along x axis, and this is the property of a linearly polarized light or a plane polarized light. Okay. Thus, therefore, this is device is called polarizer, yeah, because it is polarizing the unpolarized light. Now, suppose this linearly polarized light, say of intensity I naught, is passed through another polarizer P2, and say the path axis of the second polarizer is rotated by angle theta from the x axis. Now, this is our x axis and this is now the path axis of the polarizer P2. Now, in this case, the light component which are allowed to pass would be those whose field or field of vibration is tilted by theta degree with respect to the vertical. Okay. The law of Malus here says the intensity which we receive here would be equal to I naught cos square theta. Okay. Now, here if I ask you that if the unpolarized light has intensity I1, then what would be the relation between I1 and I naught? Can we find out, or the reframed question is that can we find out the relation between intensity or irradiance I naught and I1 using Malus law? And the answer is of course yes. But how? Because Malus law says that if the incident intensity is I naught, then the output intensity I would be related to I naught through this term cos square theta, where theta is the angle of rotation of the polarization, or theta is the angle between the polarizer's path axis. But here we do not have two polarizers. Okay. But do remember, this theta is not only the angle between the two path axes of the polarizer, theta is angle between the electric field oscillation direction. The electric field before polarizer P2 is oscillating along x axis, while the electric field after polarizer P2 is oscillating along an axis which is oriented at angle theta with respect to the vertical direction with respect to x axis. Okay. This vertical axis is at angle theta with respect to the vibration of final field. Okay. Now, here the problem at hand is that we need to develop a relation between I naught and I1. Okay. I1 is the intensity of unpolarized light, and in unpolarized light all the orientation of field is allowed, while I naught is the intensity of light which is linearly polarized, and the field in this linearly polarized light is oscillating only in vertical direction along x axis. Then how to calculate theta here in this case? In this case, we will again implement this Malus law, which says I naught is equal to I 1 cos square theta, but cos theta here is the angle between x axis and the direction of oscillation of field in unpolarized light. But we know that in unpolarized light, field changes its direction of oscillation, its orientation is random. Okay. Therefore, in unpolarized light, the direction of oscillation is a time dependent function. Therefore, here we will take time average of theta, of cos square theta, and if you think of this, then time average of cos square theta is average of cos square theta with theta, or let me reframe it, the average of cos square theta we will take because things are time dependent in unpolarized light, the electric field is changing in orientation randomly. Therefore, the all possible values of theta are allowed, okay, all values of theta are allowed in this case. Therefore, we will have to take average over theta, okay. Instead of writing time, I am now writing theta, we are taking average over theta, and if you take average of cos square theta, then you will get half, okay. Therefore, the relation between I naught and I 1 would be this, I naught would be I 1 by 2. Okay. Now, if the polarizer P 2 is now rotated in clockwise direction, then intensity will increase until the pass axis of the polarizer is parallel to x axis. Okay. A further rotation will result in a decrease in intensity and until the pass axis is parallel to y axis, where the intensity will be almost 0. Okay. And this can be understood easily, yeah, because after polarizer P 1, this is P 1, we have this linearly polarized light, and this is the pass axis of polarizer P 1. Now, this we have a polarizer P 2 here, whose pass axis is oriented in this direction, say, and therefore, here at the output we are getting this type of polarization. Now, if you rotate this polarizer P 2, then what will happen is its pass axis will rotate along with this polarizer, and when this pass axis become parallel to the x axis, we will see maximum intensity, and this happens twice in 360 rotation. Therefore, at the output, if you plot the relative intensity with respect to the angle of rotation, then you will get the sinusoidal type pattern. Okay. The intensity will be function of theta, and it will follow this sinusoidal variation, because we are plotting effectively cos square theta function. Okay. And this is not 0, yeah, the 0 is somewhere here. Okay. This is the 0 because it is a cos square theta function, okay, because I is equal to I naught cos square theta. Okay. So, this is cos square theta function. Now, this start value will depend upon this angle, the relative orientation of the pass axis of the polarizer P 2 and the direction of oscillation of the linearly polarized light which is falling on the polarizer P 2. Yeah. Hope this is understood, and this is all for today. Thank you for being with me. See you in the next class.